So we've had a little bit of a, just a bit of a break since I taught last. So I want to do just a bit of a refresher to kind of recontextualize where we're at. Because I know you all changed gears to stat stuff with Tovio, and we're changing gears back to this. So I'm going to do my overview again. So last time we went through the major topics that we went through were we sort of dove deeper into strings and we introduced dictionaries. We didn't have time to get through tuples and sets. Those shouldn't take too terribly long though. So, and then we're going to be going in. So that's what we're going to do today. We're going to go into tuples and sets, and then we have some material on more data structures. We'll be talking more about sets, tuples, and dictionaries, and lists, and comprehensions. Cool. So in terms of where everything fits together, last time we talked about strings and dictionaries. Those are different data types built into Python. They go with, well, lists are mutable, so they're going to go with dictionaries there. Strings are a collection of characters, but they are actually immutable. Tuples, which we're about to talk about, are basically immutable lists. And then sets are another mutable type. They're a bit of an outlier, as we'll see in terms of the types. They're another type that's a collection of other objects. So yeah. And then we have our functions, conditions, and loops to give us a complete view of programming. Cool. So let's do a quick sort of, wonder if we can just go through the review stuff on dictionaries. Okay, let's go through the dictionary review stuff real quick. So review, what is a dictionary? Dictionaries contain key value pairs in a mutable, unordered collection. Keys must be immutable and unique. Dictionaries are declared using curly brackets. So the syntax is we put our dictionary in curly brackets, and we separate the key and the value with a colon, and we separate the pair, key value pair, each key value pair we separate with a comma. The key has to be some immutable type. The reason for that is that the key is hashed, and if you made a hash for a type that's mutable, that type could change. You undo the hash, and then you don't end up with the changed type, right? So if we had a list and we mutated the list, if we hashed the original list, the hash can't change. It wouldn't make sense for the dictionary to have a changing hash or rehash that type. So it's going to hash it once, leave the hash alone. You could delete the key, which would delete the hash, but yeah, if we hash that list and then change the list, then the hash no longer refers to that list, which gets confusing. Therefore, the keys have to be immutable types, and this is a similarity. We'll see that sets have a similar behavior around their elements. You can think about, we'll look at this in a second more, but you can think about a set as a dictionary with no values. So it's a dictionary with only the keys. It's sort of similar to that. So sets can only hold immutable types. And then the values of a dictionary, the values are any other data type, any value whatsoever. The value could be another dictionary, it could be a list, it could be a tuple, it could be none, it could be a string or an integer or a bool or whatever, or a set. There, that's everything. Okay, so we got a little breakout here. Let's see. Okay, that's the solution. I want to pop this in, and y'all can go through it. One second here. Okay, oops. There you have it. Do feel free once you get an answer to paste it into Slack in a formatted code cell. Okay. Go ahead. Go ahead and put in your answers, whatever you got. Well, let's look at a solution for this. Ah. Okay. Here's our problem statement. Cool. So write a function that prompts the user for input, or that prompts the user to input numbers separated by dashes. Your script will take those numbers and print the directory where the keys are inputted numbers, and the values are the squares of those numbers. So the keys are the numbers put in by the user, and the values are the squares, right? So remember that, oops, oh, these are non-ASCII characters, dang it. These are gonna mess up my interpreter. Okay, that should work, okay. So here we have an example, and we can turn this into a test. I'm gonna build this in a different kind of way than exactly how they're asking. I'm not going to use input. Instead, I'm going to take in an argument. There's a couple questions like this, or maybe this is the last one, that were not that were written before I was teaching premium prep. I generally don't like to take in input in a function as much, unless that function's explicit purpose is to take in and validate a specific kind of input, like an email or something. That makes sense to me, but in general, I don't like to do that. But we still have this in here. I decided, well, it's good to keep this around because it gives me an opportunity to talk about this thing. Okay, so this is what we expect. And did this function have a name? Let's see what it called it, square dict. Okay, so print square dict with inp. And now we'll def square dict. We'll take in num string, and we're still going to assume that num string is formatted in this way. So we'll say num list equals num string dot split. And let's just iterate through num list, make sure, oops, for num and num list, make sure we have num correct. Okay, we still have our dashes, right? So I don't want to split on spaces this time. I want to split on space dash space. Oops, I did that backwards. Space dash space. Space. It's like a tongue twister. I'm failing to say that. Okay, cool. We're getting a couple nuns here. Where's that other nun coming from? Oh, why I'm printing print? What am I doing there? I don't know what's going on there. Okay, sorry about that. That was really weird. Okay. Cool. So these are each of our numbers. Let's just do this real quick and just put this in a list to show us something that if you have a string in a list, it'll put the quotes around the string. If it's not in the list, it'll just show you the contents of the string. So I just put it in a list to show us that these are actually the numbers of the characters of the number, of the digits. They're digit characters. They're not actually numbers. So we need to cast these as ints, which I'll do in the list just to prove that these are now ints. Okay. So if we want to use those, we want to cast them as ints. Okay, so we can say d sub int num equals int num squared. And since I'm adding to this dictionary, I better make it exist first so that Python knows it's a dictionary that I'm adding to. And then we can return D. Cool. This comes out in a little bit of a different order than the input, but again, you know, it will come out in an order, but the order is trivia with a dictionary. The order is not as important as it is with a list or a string or a tuple. But these should have the same key value pairs. Cool. Okay. And then, yeah, looks like the solution is just what I had. I think I want to skip this in the interest of being able to get through everything since we have a little bit to get through. Okay. Cool. So we'll come back to this. So that's good enough, I think, for some dictionary review. Let's get into tuples and then sets. Okay, so the thing here to remember with tuples, we're changing gears into tuples now. The thing to remember here with tuples, tuples are very much like lists. There's a lot of things that you can do with a list that you can also do to a tuple. They are ordered collections of arbitrary objects, meaning that we can mix and match, have, you know, we have a tuple containing a list and then another tuple and a dictionary and string and integers. We can mix and match types to our heart's content. They're ordered, which means they have an index starting at 0. Being that they have an index, we can index into them to select a specific element, or we can slice a portion of the tuple. In the slicing rules, behave exactly the same, whether it's a tuple or a list. So the difference is tuples don't have any tools that change their values or that alter their values. So lists have things like append, extend, and we can actually, there's kind of a easy little exercise here. If I just do dir list, directory of the list, and let's just grab the regular named methods. Okay, now let's treat this like a little breakout. And I want to use this as an opportunity to get a sense of where you're at. So if you're, you know, give this a shot, but if you don't know, let me know. Be like, I'm at a loss. I don't mean to put you on the spot, but if you feel comfortable doing that and saying like, I don't know this one, let me know. And that'll tell me that I need to like focus on mutability more as we go. But so the idea here is these are all the methods for lists, all the regular methods. There's these dunder methods, which I'm just going to tell you to ignore for now. These are all the regular methods for lists. So tuples have methods, but they don't have any of the mutable methods. If I took away all the mutable methods from a list and just took away its ability to have mutations, and so that'd be all the mutable methods plus item assignment. We'll get to that in a second. then they would be tuples. So the question to you is, go through this list of list methods, and we paste this in, and repaste all the ones that are immutable. So when you repaste it, delete all the mutable ones from that. I'm hoping that's clear. I'm hoping the question I'm asking is clearly stated. Okay, cool. We got a number of answers here. Awesome. So I'm seeing a lot of people putting in copy, which is, it's a bit of a curveball because you're right, copy doesn't change the list. So it doesn't cause a mutation. So you definitely get off the hook with that one. That was the question as I stated it. So yes, correct. Copy does not mutate the list. However, dear, I think we can just do this. Count and index are the only, this is the directory for a tuple. Count and index, that's it. Why don't we have copy? And this kind of gets at the heart of the difference of a mutable versus an immutable type. So go ahead and put an answer in there. Why do you think we don't have copy in a tuple? Because it would change the location? Well, it would give us a different object at a different location. Yeah, that's all I'll say for now. Copy gives a new object. Yep. Why would we need a new object if we had an immutable type, though? Like what's the use of having a copy method? Yeah. Yep. Cool. Yeah. So immutable types. So I'm getting a lot of good answers here. So I'll just read them out. The reason, the first one here is the reason. Well, there's two that are, the first two are changes the location and gives a copy of a new object. So yes, that's what copy does. And that's useful when the type you're working with has the ability to change. It's nice to be like, okay, well, maybe I'll make a backup of this or duplicate this so that I can alter one without altering the original. So yes, and then we got the reason the copy is made is because the next step is to mutate the object, because tuples are already immutable. Yeah, because you're going to change the copy so you don't alter the original. Yeah, so that's why we make a copy, is to avoid altering the data in a place where we don't want to alter it, and alter it in a place where it's okay to alter it. Tuples don't have this capacity, so we just don't need to worry about it. Another way you could sort of think about it, like if you make any sort of, it's called a transform rather than a mutation. So I'll show you. If I have an empty tuple, I'm just going to call it tup. We'll say tuple like this, and then we'll say tup plus equals right. This sure looks like an append if you think about it. Right, this sure seems to have the effect of an append. Where's my? Whoops, is this not? Okay, oh, there it is. Okay, so first it's empty and then it has hello in it. If you have a single element tuple, by the way, you have to put the comma after it. It looks really unnatural, but it's the way it is. If you have no elements in a tuple, then Python knows, oh, parentheses, it's a tuple. If you have one element in a tuple, then it thinks it's an expression group. It thinks you're using the parentheses to group an expression. So you have to put a comma in it if you have one. If you have two, obviously you have to have a comma to separate them. If you have none, it can tell it's a tuple just by the fact that it's not an expression group because there's nothing in it. But if you have one element, there has to be a comma at the end. So that's why that's there. So this sure seems like an append, but if I look at, let's do this. So if I look at the IDs, we can see the IDs are different, right? So we didn't actually append to this tuple. We just said tup equals empty tuple. Now tup equals empty tuple plus tuple with hello in it, which is itself a different tuple. So this just gives us a different data structure back. So you could kind of think about this like, if you needed an analogy, it might be a little bit of a stretch, but you could kind of think of a tuple as a kind of a self-copying type. And I'm pretty sure if I do tup2 equals tup, I'm pretty sure that this will give us a different ID as well. We can look at this though. Python will tell us. Ah, no, that is, yeah, that's just a raw pointer. But yeah, if we did, let's try this. Let's add hello to tup1 and see if we change tup2. We don't, yeah. So even though this is still a shallow copy, this is an effective copy to the tuple, because any attempt to change the tuple whatsoever results in a different object in memory, results in a different ID. So it won't change tup2. You can see that. So not having the ability to mutate sort of gives us, we kind of don't, I mean, in a way, we kind of don't lose anything, right? If we can do an append like this, and yeah, I mean, we could even go through these, right? These are all the methods for lists, right? And let me make sure, let me make this clear. These are all list methods, but we saw how we can do it, something that is, we can manipulate the pointer like this to sort of mimic a behavior of an append. If I had hello in my tuple, hello like this, I could append to it. We saw that. Clearing it, tup equals empty tuple. That's kind of tantamount to a clear. Copying kind of self copies. Count already exists for tuples, so that works exactly the same as it would for lists. Extend, well, extend for tuples is, if we want to mimic this behavior in lists, I mean, it's just a concatenation. It's exactly the same as the sort of as mimicking append, except you add more stuff to it, and that's similar to an extend. Index exists for tuples. Insert, we can do something with slicing that will mimic an insert behavior. So I might say tup equals, let's say I wanted to insert at index 1, I wanted to insert, I don't know, hey, something like this. So we could say tup sub, we'll do a slice to index 1, 0 to index 1. That'll include 0, but not index 1. And then we'll concatenate that against a tuple that contains hey, this is the thing we're inserting. And then we'll slice the rest of the tuple back together. Oops. Plus tup1 to the end. And we'll print tup. Yeah. Okay, so hello, hey, and more stuff, right? So we inserted hey, right? So I'll spare you going through each of these, but you can essentially mimic the behavior with slight concatenation, slicing, and indexing. Those 3 things, if you get good at them, and see, this is concatenation and slicing, right? We have slices of tuples, and we're concatenating those against other tuples to mimic the behavior of the other ones. And what you're doing is you're doing a transform on the value of tup and then just resaving it in the same pointer. And it seems like, it kind of feels like a mutable type without the danger of a mutable type. So I was waiting for this lesson because somebody earlier in the class asked, why would I, if tuples are immutable, like why use tuples? Because essentially, like you can still do whatever you want with them. You're just doing it through transforms and getting a different object every time. So there's a potential. I mean, I think the argument is that one way may be more computationally efficient than another. But tuples are safe, like they're consistently safe. They're consistently predictable. So that may also be an advantage, right? So yeah, so there's slightly different tools that work slightly differently, and you may choose one or over the other, but they're, at the end of the day, they're basically pretty comparable. So okay, cool. Let's go over this just for good measure. Tuples are ordered collections, so ordered, indexing, slicing, zero-based index, etc. Very similar to lists. They are immutable, declared using parentheses, and they only have two methods, which are count and index. Declaring tuples. A tuple with multiple things in it is just like a list with multiple things in it. An empty tuple, except with parentheses instead of square brackets. An empty tuple is, again, just parentheses. A tuple with a single element in it is a weird one because it's the element followed by a comma. So an empty tuple can have zero parentheses or zero commas, but if it has one element, unlike a list, you still have to put a comma after the element, so it knows that it's not just an expression group expressing the value 1. So that's so Python can distinguish between expression grouping and tuples, since the parentheses operator is overloaded. Overloaded just means it does multiple things. One job that parentheses has is, well, to determine the inputs of a function, the parameters of a function definition, the arguments of a function, expression groups, and tuples. So parentheses do quite a number of things in Python. Tubal immutability, we basically covered this. So once a tuple is declared, it generally can't be changed in any way. And I would even delete generally, like it can't be changed. The pointer can be changed. We can concatenate it against something else, but we get a different object. So we're never changing any objects. We're never changing any tuples. All that tuple manipulation you saw me do didn't change a single one of those tuples. But it gave me different versions of combinations of tuples. So we can do that, but they result in different objects, of course. So however, if an element is a tuple, if an element within a tuple is mutable, the element can be changed, right? So if a tuple holds a list, the list can be altered, right? So the objects within it still obey whatever rules that those objects are designed to work with. Tuples, so this is a way of thinking about it. Lists in your memory, you have your registers in your RAM. Somewhere there's a register that says that there's a beginning of a list, and then the elements after that register are the elements of the list, and then there's a register in your RAM that says the list, there's a closing to the list. The list is over, right? So a list quite literally holds the elements. A list holds the elements within it. I talk about tuples that way, although it really is technically a misnomer. A tuple doesn't ever hold an int or a list or whatever. It holds references to those objects. So much like a variable is a reference to an object, it doesn't contain the object, it references the object. A tuple holds pointers or references as well. So that's another way of thinking about it. Admittedly, I do. We will kind of talk about it in terms of variables holding a value or tuples holding values, whatever. But in truth, that's just sort of a misnomer that we all know. One of those things where we all know it's kind of a little bit wrong, but it makes sense anyway, so we just do it. Okay. Let's look at that. Breakout doesn't have a solution. Cool. Yeah, let's move on to sets. The set data type. So sets are unordered, mutable collections. So sets are, like I said, sets are kind of the weirdest type that we've introduced thus far. So dictionaries, I would say, are maybe the most complicated. They're not terribly complicated, but since you have to explicitly manage keys and values together, there's a little bit to learn in terms of managing that. So they have more, let's say, moving parts. There are a little more to them. Sets, I would say, are kind of simpler, but they're weird. So sets are unordered, mutable collections. Sets will only contain unique elements, meaning that we cannot have duplicates. So a set can't contain duplicates of a given item. I should probably go back and change this as well, but a set also can't contain mutable types. I talked about this earlier at the beginning of this lesson. So let's make a set. So the way we make an empty set, you can use curly brackets in some cases, although Python will often become confused and think you meant to use a dictionary. So don't use curly brackets. Use the set constructor function like this. So you make an empty set like this, and then we can add elements to it. I'm just going to cast a list as a set. So if I want to make a set literal, I'll usually just do this because that's my habit. Okay, so I have 33 at the beginning and the end here. Oops, why am I calling it set? I can't do that. So I just broke a rule here, right? Set is the name of a built-in function, and so I can't really. Python will let me call this variable set, but I really shouldn't. So let's do that. Okay, so unique elements. Let's look at this idea of unique elements. So this is what a set looks like when it gets returned, surrounded by curly brackets. And this actually will work as a set literal. But still, I like to do it this way. I'd like to just cast a list as a set when I'm making a set literal. Just, I don't know, personal preference. So notice we have 33, 5, 22, 7, and 33 again. This has 33, 5, 22, and 7. Right, so it didn't so much remove this 33 just so as it just realized both, or let's put it like this: 33 and 33 both hash to whatever 33 hashes to, and sets hold the hashes, and then they reconstruct the data type based on those hashes. So since all of the elements in a set are hashed, they can't hold duplicates because two items will hash to the same thing. Unordered, we are getting the elements back in the same order that they went in the list. And for a while, I was getting sorted sets. Maybe that was in Replit. Anyways. Cool. So sort of a weird thing about sets being unordered. Dictionaries are unordered, but we can retrieve elements back from a dictionary because they have a key. Lists and tuples and strings are ordered, so they use indices so we can retrieve elements and slice sections of them with their indices. Sets have neither indices nor keys. So how do we retrieve elements from a set? And the answer is sets are not useful for storing items that you intend to retrieve again. I tend to think about things like you use lists and then you turn them into sets when you need to do set operations or when you need them to be a set. So so I kind of think of sets a little bit as kind of a little bit of a secondary importance, because I tend to just use lists and then only cast them as sets when it makes sense to do so. And let's look at the set operations that kind of make them useful. So one thing, this isn't mentioned in the material, but I saw a really interesting Python problem, Python problem in Code Wars that had you, it's a really simple problem. I can't totally remember it, but it was like return it's something to do with like find the index of the smallest number in a list or something just simple like that. And I kept getting timeouts on it, and it kept running over time, and I realized at some point, well, I could just cast it to a set and then find the smallest element that way. But I'm not totally remembering the problem, but the gist is that I had this huge space that I was checking. It was like one of the tests was a list with like a million elements in it or something. It was just this huge list, and it was taking too long to go through. But all but one of those elements were the same. So if I cast them to a set, I would just have two elements. So that made that operation very easy. Oh, I think actually that might have been the problem, is to find the different element. Yeah. Anyways. So that's another thing that sets are useful for. Potentially, if you have something that, that's massive, but it's only massive because there are lots and lots of duplicates of various things, you may be able to reduce its size down significantly, casting it as a set. So if you have a giant list that has a ton of duplicates, you can reduce it down to only unique elements with a set. That's one scenario where a set's very useful. Removing duplicates, another scenario, right? Sort of independently of that, although related. And then we have set operations: union, intersection, and difference. So let's look at these. So the union and intersection methods in sets are similar to their mathematical analogs. The union is a set of elements in two sets. So let's just look at this. Okay, so notice these sets have some things in common, and they have some things that are different about them. And actually, why don't I'll remove this duplicate here. We'll do that. So the union, if I do the union of set1 dot union set 2, and the order doesn't matter. It could be set 1, set 2, or set 2, set 1. The order doesn't matter. So I'm going to get basically a combination of both of these sets. So this is going to contain all the elements in both without duplicates. So here you can see we have a single instance of every element from both sets. Cool. So that's union. Intersection are the elements that it has in common. So set 1, intersection, set 2, 5, 22, and 7. So notice I put the 5, the 22, and the 7 right here so we can see that those are obviously in common. Anybody want to guess what difference does? That's right. It tells you what's different. So difference probably, I'm going to guess probably most of you know this, but the result of a subtraction operation is called the difference, right? Happily, you can use the subtraction operator on sets like this for the difference. And it's directional. So the difference of set 2 difference of set 1 is different from set 1 difference of set 2. So set 1 minus set 2 gives us something different from set 2 minus set 1. So set 1 minus set 2 gives us all the elements that are in set 1 minus the elements that are also in set 2. So it's all the elements that are unique to set 1. So we should see 33 and 44 there. And then likewise with set 2 minus set 1 is all the elements unique in set 2 that are not present in set 1. So union, intersection, and difference. Difference is directional, the other two are not. And these are sort of the major reasons for casting a list to a set. If you do want to, because I know some of you, and there's a case to do this. My set. If you do want to use a set directly, like an empty set, and you want to use it without like building a list and then casting it to a set later, you can say, you can use the add method. mySet.add. So add takes the place of append. So instead of using append, sets use add. Like I said, in general, like probably just use a list and then cast it as a set when you need it to be a set. But if you do want to use a set directly, you can use add instead of append. The reason it's not append is because append means to put something on the end. Sets don't have an order, so what does it mean to put something on the end if something doesn't have an order? It's like, you know, imagine like a jar of jelly beans. Like if I said, hand me the last jelly bean in that jar, you'd be like, I don't know, find something better to do with your time or something. I don't know. What does that even mean? What does the last jelly bean in that jar mean? Is that some like Zen koan or something? But anyways. So a set is unordered, so we just have a semantically more meaningful name, which is add. Cool. Okay, we're about at halfway, so let's reconvene at 2 after the hour. So let's take these questions. And I think these will kind of sum up what we just went over in a nice way. So apologies if this is a little redundant, but I think it'll kind of contextualize what we just looked at with sets. So one is, so you can or this is for tuples, so you can concatenate tuples but not append. Yes. Concatenation results in a different object. Append alters the object. So concatenation is just like, hey, what would this look like together as one thing, right? What would ABC look like, a tuple of ABC look like combined with a tuple of DEF or something like that. So you put those together, you get a tuple with both of those, and then you can just reassign that tuple to the same pointer, and it kind of seems like an append, but you're safe from altering an original, right? So there's no case in which that alters the original tuple that had ABC. So if you pass that ABC tuple into a function, you can concatenate to your heart's content in the function, and it'll never alter the original tuple. So that's the big thing there. And then another question, can I explain when you would use a set over a list? Like, is there a rule of thumb? And then somebody says for set operations, most likely. Yes. Basically for set operations. What, you might ask, are set operations? These are what I mean by set operations. And I used, just to be clear here, I used minus. This is exactly identical to using dot difference. Use whichever one you want. I think I tend to use minus, but I don't know. I don't really know which one I tend to use more. I don't have like a one that I picked that I prefer. But the difference is aesthetic. Whether you like the dot difference method or just the subtraction sign. I kind of like maybe I like the subtraction sign, but anyways, that's the same operation either way. So these are the major reasons to use a set. The other one is removal of duplicates, or to reduce the size of a list that has a lot of duplicates in it, right? Potentially to iterate through it, right? So if I have a list with 1 million elements, and I can reduce it down to it. Well, let's say if 999,999 of them are the same, and there's one different element, then I can reduce it down to the size of 2. So that's kind of an extreme example, but serves my point, so you can reduce the size down to iterate through something smaller. And then sometimes just removal of duplicates is useful all on its own, without necessarily being associated with reducing the size, right? Sometimes you just need to remove duplicates for other reasons. Yeah. So those, I would say those are the reasons to use a set over a list. If you do decide to use a set directly, you can use add. Generally, I just make lists and then cast them as sets, like I said, as needed. Oh, it occurs to me, like, you might wonder, well, if you'd only use a set for set operations, why not just make union, intersection, and difference methods for lists? And I don't know. I mean, it's sort of, you could design a language that has set operations included for a type that's similar to a list, I guess. But I think that there's sort of a paradigmatic reason. Like, it doesn't make sense to do a union or an intersection or a difference on an object that is structured like a list. It does make sense to do it when you don't have duplicates. if you have duplicates, if you have the ability to have duplicates, it raises other questions. Like how do you handle that? Do you include them? Do you exclude them? What type do you give back? Do you just give back another list? Do you give back something that is explicitly a set? You know, so you have the set data type, but it you know doesn't have a literal form. It's only the result of certain list operations. You know, so I think it makes sense for sets to be their own type and have these operations unique to them. So that's what I would say in answer to that. Then we got a question. Looks like some code here. Is this possible? List equals empty list. My set equals. Let me copy this in. Looking at this line, I think what you're doing is trying to cast this list as a set. I would just say, I know it says in our materials and you know that you can use curly brackets for sets. Just don't use curly brackets for sets. Always just use the set constructor function. This will behave differently, and we'll look at that in a second. So this will convert that list to a set. And this will reassign the pointer to be literally that same set, right? So if I print list and then print my, come on, my set, and then print list again. So we'll see that set copied twice, right? The reason the curly brackets won't work, it's kind of weird. So lists are mutable, are a mutable type. So I can't have a list as a member of a set anyways. I can, you know, there's an obvious analogy to be made between a list and a set, but I can't have a list as a member of a set. I can turn a list into a set, but I can't have a list as a member, as an element in that set. So this kind of syntax, imagine this with a list. This isn't, or imagine this as a tuple, right? This isn't, hey, cast that list as a tuple. It's take this list and put it as an element in a tuple. Well, it would be if we had a comma after it, right? Same thing like this. It's not, hey, cast this list as a list. It's take this inner list and make it its own element in this outer list. So we would have a nested list here. So that's what's happening with that. So when I see curly brackets, the behavior would be that you had, you know, a set of with some elements in it like this, right? Oops, sorry. There we go. But that won't work because it can't hash a list anyways. Well, let's just look at the error it gives us. So it says type error, unhashable type list for this. This is a good question. I hope, I worry that like I feel like I'm like, you know, I don't mean to like tear apart your question. This is a good question, and this is really worth exploring because, yeah, this actually gets at the heart of like how and why sets work the way they do, right? Lists are unhashable types and things like that, right? So you could do, if you really don't want to use the set constructor function and you have some elements that you want to put in a set and you really want to use curly brackets, against my advice, which you know, you don't have to take all my advice, but it's great advice, really. It's top tier. You could do this. This is going to work fine. This is going to just put these elements in a set. The problem is, the reason I don't like to encourage people to use curly brackets ever, just make it a list and then cast it as a set with the function. The reason I prefer this is if you take it as consistent that curly brackets are going to behave as a set, well, they will if you put elements in them. So Python knows this is a set. So what's this? Is it a set or a dictionary? So the answer is it's a dictionary. Python makes the assumption that if it sees empty curly brackets, that's a dictionary, not a set. So if I try to do something like my set equals curly brackets, my set dot add hello, it'll say dictionary object has no attribute add. Attribution error. Right, so that's why, for the sake of consistency, yeah, if you have a set literal, you want to, and you know what elements you're going to put in it, and you're literally going to write in those elements, then sure, you can use curly brackets. But curly brackets no longer work when you're starting with an empty set. If you want to start with an empty set, use that set constructor function. If you want to, and for the sake of consistency, just having one set of tools rather than multiple sets of tools for weird different circumstances, just cast a list as a set like this. If you want to put stuff in it, that's my opinion, but you can do what you like. Y'all are adults, so make your own. You can make your own decisions. Okay, cool. Good questions, though. Love the questions. Somebody says cast question mark and then set list like this. Yes, this is casting a list as a set, presuming that list existed like it did up here. We could say converting, but it doesn't change, converting doesn't change that list from a list into a set. It's a transform operation rather than a mutation operation. So the word is cast, which sort of, I guess, feels less like a permanent thing. Doesn't alter the original list. It just gives us a set version of that list. So yeah, that's what cast means. And then somebody has some code here. Cool. List equals empty list. My set equals tuple of a list. Oh, ignore the code. Okay, cool. All right. I was like, what's going on here? But yeah. All right, let's move on. So this has some review in it, which we can skip because we just went through the stuff. So I think we might just be left with breakouts. Let me just go through this really quick. Maybe I'll just try to do all the breakouts. Well, that sounds kind of crazy. Yeah, let's just let's pick one of these breakouts and go through it. Let's do this one. Actually, I'll do this. That's part one. Sorry, I should have done this. Let me change this to be one message. Add a message. There we go. All right, and I'll put 4 minutes on the clock. Now feel free to get started. All right, go ahead and put in your answers for this breakout. Cool, and you can look through the solution in the slides on your own. Okay, zip. We've got a little breakout for zip here. We covered zip a while ago, but this is a good one. So you know how to iterate over a single data structure. What if you have parallel lists? How can we iterate over these at the same time? You know, I just said we covered zip a little while ago. I'm not sure that we did. I know we covered it in study hall, and I'm worried that I'm getting that confused. So zip, there will come a time where you have two things. Let's do names equals a list of Sally, Bob, and Jill, and favorite colors equals, oops, red, black, and blue. So if I want to iterate through these, there will come a time where you're going to have two lists and you want to iterate through them simultaneously. Zip is the answer for name, color, and zip, names, favorite colors. Print name, favorite color is, okay. So Sally's favorite color is red. Oops. Sally's favorite color is red. Bob's favorite color is black. And Jill's favorite color is blue. Cool. So that's zip in a nutshell. Okay, so here is another breakout. Let me just convert these parts. Cool. There's another one. We got 5 minutes on the clock. All right, while those are coming in, I will show mine. Okay, so I decided to be a right fancy lad with this one. Apologies. Here's my test. I just called my function tupleizer. We take in the strings. We expect the list of tuples. Notice the contained elements within are integers. So it's a list of strings of, excuse me, it's a list of tuples of integers. Okay. So in order to get a list, so what I'm doing, well, I'll work backwards here. So here's my expectations. So what I wanted to do was I wanted to zip a list of the numbers. A list of every other number starting from the 0th index with a list of every other number starting from the first index. Basically, that's what's going on here. So I'm zipping numList sub : 2. So every other number starting and including with 0, starting with and including 0. And then every other number starting with and including 1. So that's going to be the list basically staggered against itself. And I can pass the elements to zip in that manner. Zips are going to zip them together, give me a tuple out for every one of its iterations. It does not return a list, so I have to cast it as a list explicitly, like that. And then in order to construct this numList, just so I don't have to write this part twice, so I don't have to do this like that, because that's just a mean, nasty line of code right there. I can break that into a variable and just do it once. So this is, first we split the string. And we split it on comma space, which is our delimiter for each number. That will give me a list of digit characters. I want to map each of those characters to int so that they're actually integers, as per is represented in the output. So I use map and map the int function to each one of those digit characters, and then I just cast that as a list because, again, map does not give us a list back. You know, I just realized I don't think I do have to cast this as a list, but I should probably rename this like nums or something. Yeah, so we can do that. I think that'll work just as well. We'll see. Oh, right. Yes, of course, because map object is not scriptable. I went I went through that once as I was writing it, and then I looked at it again and I was like, oh wait, I can do this. And oh right, no, I can't. Okay, cool. I see one answer. If you don't have a complete solution, go ahead and just share your code anyways. Just it's nice to get a sense of how people are thinking and share your thoughts. Nothing else. So. Real quick here. Okay, good. All right. We are running light on time, but we have enough time to, I mean, we're basically going to make it through everything, which is pretty amazing. We're not going to quite make it through everything with comprehension. So I want to be clear about where comprehensions fit. In the overview that I do at the beginning of every class, types, functions, conditions, loops. So with loops, we have for loops, we have while loops. I'm calling this loops just to make things easy. Really, I should call this iterators, because there are other non-loop iterators. Map is actually a non-loop iterator. So map is another iterator that we've learned, and comprehensions. There are two types of comprehensions: list and dict comprehensions, list and dictionary comprehensions. So these are both the types of comprehensions. If you want a set or a tuple comprehension, you do a list comprehension and cast it accordingly. Sometimes, well, quite often I've done like a string comprehension, which is where you do a list comprehension and then you pass it to join, and you join with some delimiter. So you can do that. So that's for that. And then dictionary comprehensions are just dictionary comprehensions. Okay. So this is where in the overview, in the whole equation of where everything fits together, comprehensions fit here. Map and comprehensions are really cool ways, potentially very elegant. They make for clean code potentially, and potentially also optimized solutions. Python can do certain things behind the scenes to optimize map and comprehensions for certain problems. Occasionally, they will be slower depending on the problem, but usually for most problems that you can use map and comprehensions for, most kind of regular problems that you can use maps and comprehensions for, they will be optimized. They will have a slightly better runtime than for while loops. So remember the relationship with for or while loops. Let's kind of put this in a hierarchy, right? In terms of like power. And I don't know if I would put map above comprehensions. Really, I'd put these on like the same level, honestly, but we'll just do this for now. But while loops are the most powerful, technically, and we're not going to cover recursion. If you want to go look into recursion on your own time, it's fun, it's cool, you don't need to worry about it for now. While loops are the most powerful, though, of the ones we're talking about. I'll delete recursion. For loops can solve a lot of problems that while loops can solve. Most of the time, the kinds of problems that you need a loop for, I probably shouldn't say most of the time, but quite very often, for most types of coding, for most domains of programming, you'll find that you can use for loops in most circumstances. Map and comprehensions are sort of a subset, again, of for loops, right? So we can use, and I'll get map out of there because I'm not really talking about map. We sort of think of map as a different thing. It is technically an iterator or an iteration structure, but we'll just keep it local to comprehensions for now. So comprehensions can solve, so just like we say, a for loop can solve any iteration problem provided we know how many iterations is necessary before we start looping. So if we can determine the number of iterations, or if we have a list has a fixed size. It can grow and change, but it has a fixed size. So if we can determine the number of iterations before we start looping, we can use a for loop. If we can't, we need to use a while loop. If information does not need to be passed from one iteration to any successive iteration, we can use a comprehension. Okay, so a comprehension, a for loop can solve any problem a comprehension can solve, and a while loop can solve any problem a for loop or a comprehension can solve as well. So comprehensions are, I would say, a little less powerful in terms of, and I mean powerful in terms of the versatility, the amount of problems that they can solve, right? So comprehensions are a little bit less powerful, but since they're a little bit narrower in their focus, they can be optimized for the problems that they can solve. So for the problems that they can solve, they tend to be to gain a slight optimization. I've never been able to like really turn the tables on a, sometimes you'll get code wars problems that, it's an easy solve at first, but you'll get timeouts, kind of like that problem that I was talking about before, where you have a relatively simple problem, but you'll get a timeout. So they're trying to push you in the direction of optimizing. I've never been able to satisfy one of those optimization problems by turning a for loop into a comprehension. So it tends to be what I would consider a slight performance increase, if anything. Occasionally, I've even seen comprehensions actually cause a performance decrease, but that's not that common. The way that I think about them, so if it's a moderate or kind of low performance increase, if any, if maybe even a slight decrease, why use them over for loops? Well, they are really cool. They make for some elegant code at times. So basically, if we have a list accumulator problem, we can turn that into a comprehension. Most list accumulator problems, or many we can. So I'll just write a list accumulator as a for loop. Excuse me, gosh. And we'll say for num in, and I'll just do a list literal here. These numbers, we'll say list dot append num squared. So this is a simple loop. And it'll make for a nice, simple comprehension. And actually, I'll show you how to, this is what I always do. There's sort of a set of steps that I follow to turn a loop into a comprehension. I always just break this open and onto multiple lines like that. And then I use a shortcut key for, I think I set this as a custom key on my editor. For me, it's Option, which is Alt, up and down. I'm not sure what it's going to be in VS Code. I don't remember what it is in VS Code, but I can drag lines like this. You could like cut them and then paste them or something like that, but I'm going to drag my lines because that's what I do. And then whatever you're appending, you can just grab the thing that you're appending, not the append itself, and just put that right up front. And then take your loop head, put that right behind it, delete the colon, cinch everything up, and delete whatever's left over, right? So this takes a simple for loop and makes it even more elegant, right? This is not an elegant code. I don't think this is clunky or ugly looking or whatever. This is nice and simple, and this is like even simpler, even nicer. So sometimes you have like a really simple loop you want to do, and you just want to do it in place. You can get it on one line, and it's nice and elegant and simple and really good. Yeah. So obviously, I like I like comprehensions, so we can do that. So these are what I would consider logically identical, even though we're using different tools to achieve the same ends. Like we're solving this problem in the same way. In either case, we're just have an accumulator essentially. So so a list comprehension is like a list accumulator pattern kind of rolled up into one line. We're basically out of time here. I don't want you all to, so just to be clear, there are ways of adding conditions, if and else, to comprehensions. If you have an if and elif, else, or if else structure, the way you add that in is different than if you have just a solo if. So the rules around adding conditions to comprehensions get funky. They get kind of weird. So be forewarned. if you're ready to get into comprehensions, I think you're ready to go out and like learn what those rules are. This won't be on the TI. The reason we teach it is because, well, they're cool. If you need a challenge, here's something that you can grow into, and you will see them. I generally like the sort of the norms of the Python specifications and PEP 8 and things. One thing that I personally disagree with is that, officially speaking, the most Pythonic iterator is a comprehension. This is officially canon in the Python documentation that comprehensions are to be used wherever they can be used. I don't personally agree with that. It doesn't take some code that is not that complicated in a for loop becomes pretty weird in a comprehension. You can write a comprehension that can get really hard to read. I mean, I guess granted, if you read and wrote comprehensions exclusively all day, day in and day out, they'd be fine. I can read them, but I kind of do write comprehensions day in and day out. Like I see them constantly. So, but for the purposes of premium prep, for the purposes of if you're new to programming, these you can remember this. Like they can make fairly simple code even simpler and elegant, and they can sometimes make complicated code even more complicated. So take it with a grain of salt. You don't have to focus too heavily on this, but it's just something that's worth knowing because you will see it out there. Like if you go on Stack Overflow, you'll see people doing comprehensions, or Code Wars, you'll see comprehensions all over the place there. Cool. All right, so that's a good place to wrap up. Sorry for going over time. Y'all are free to go. We'll wrap up there, and I'll stop the recording.